Welcome to this comprehensive presentation on understanding consteval in C++20. Today, we'll explore this important feature that was introduced in the C++20 standard, which provides developers with a way to guarantee compile-time evaluation of functions. Consteval represents a significant evolution in C++'s compile-time programming capabilities, offering stronger guarantees than the existing constexpr keyword. By the end of this presentation, you'll have a solid understanding of what consteval is, how it differs from constexpr, and how to use it effectively in your code, and the various patterns and best practices that have emerged around this feature. We'll also look at some common pitfalls to avoid in real-world applications where consteval shines. Now, let's look at the syntax and basic usage of consteval in more detail. Declaring a consteval function is straightforward. You simply add the consteval keyword before the return type, similar to how you would use constexpr. In this first example, we have a simple square function that must be evaluated at compile time. When we call this function with a constant expression like the literal 5, it works fine and produces a compile time constant. However, if we try to call it with a runtime variable like y in this second example, the compiler will generate an error. This is because consteval functions require all their arguments to be constant expressions that can be evaluated at compile time. It's worth noting that consteval can only be applied to functions or function templates, not to variables. For variables, you would use constexpr or constant depending on your needs. Also, a consteval function cannot be called from a non-constant context, which is a stricter requirement than constexpr functions. Now, let's look at the syntax and basic usage of consteval in more detail. Declaring a consteval function is straightforward. You simply add the consteval keyword before the return type, similar to how you would use constexpr. In this first example, we have a simple square function that must be evaluated at compile time. When we call this function with a constant expression like the literal 5, it works fine and produces a compile time constant. However, if we try to call it with a runtime variable like y in this second example, the compiler will generate an error. This is because consteval functions require all their arguments to be constant expressions that can be evaluated at compile time. It's worth noting that consteval can only be applied to functions or function templates, not to variables. For variables, you would use constexpr or constant depending on your needs. Also, a consteval function cannot be called from a non-constant context, which is a stricter requirement than constexpr functions. This slide compares constexpr and consteval in depth, which is crucial for understanding when to use each. The key difference is that constexpr means a function may be evaluated at compile time, while consteval means a function must be evaluated at compile time. With constexpr, if you call the function with runtime arguments, it will simply be evaluated at runtime. The compiler will not produce an error. But with consteval, such a call would result in a compilation error because it violates the guarantee of compile time evaluation. This distinction makes consteval more restrictive, but also provides stronger guarantees about compile time evaluation. When flexibility is needed, for example, when a function might be used with both compile time and runtime arguments, constexpr is the appropriate choice. But when you need to ensure something happens at compile time, for instance, to guarantee zero runtime overhead or to perform validation that must happen before the program runs, consteval is the tool to use. It's also worth noting that constexpr functions can call consteval functions, but only when the constexpr function itself is being evaluated in a constant context. C++23 introduced the if consteval feature, which provides an elegant way for constexpr functions to safely call consteval functions when the context is constant evaluated. Before if consteval, there was no standard way for a constexpr function to determine whether it was being evaluated at compile time or runtime, which made it difficult to write functions that needed to behave differently in these two contexts. The if consteval statement evaluates to true if and only if the function is being evaluated in a constant context, allowing you to safely call consteval functions in that branch. This is particularly useful when you want a function to work in both compile time and runtime contexts, but take advantage of consteval functionality when possible. As shown in this example, the function checks if it's being evaluated in a constant context, and if so, it can safely call the consteval function. Otherwise, it falls back to a runtime alternative. This feature bridges the gap between constexpr and consteval, providing more flexibility while maintaining type safety. It's worth noting that if consteval is a more reliable approach than the previously used std, is underscore constant underscore evaluated, which had some subtle issues that could lead to unexpected behavior. Understanding when to use consteval versus constexpr is essential for writing effective modern C++ code. Use consteval when you must guarantee compile time execution, such as for compile time validation of critical parameters, type ID generation where consistency across translation units is important, cryptographic hashing where pre-computing values can improve performance, or ensuring zero-cost abstractions where any runtime overhead would be unacceptable. Use constexpr for general utility functions that might be useful in both compile time and runtime contexts, flexible APIs that need to work with a variety of inputs, algorithm implementations where the same code might be used with both constant and non-constant data, and hardware abstractions where the ability to work in both compile time and runtime contexts is beneficial. A good rule of thumb is to start with constexpr and only upgrade to consteval when you specifically need the compile time guarantee. This approach gives you flexibility by default while still allowing you to enforce compile time evaluation when necessary. It's also worth considering the impact on compilation time. Consteval functions can increase compilation time since they must be evaluated during compilation, so use them judiciously in performance-critical compilation scenarios. Consteval works well with template parameters, enabling powerful compile time computations. In this first example, we see a consteval function that generates type IDs at compile time based on the size of the type. This pattern is useful for creating type identification systems that work entirely at compile time, with no runtime overhead. The function uses sizeof to generate a unique ID for each type, which is evaluated during compilation. The second example shows a more advanced use case with recursive template instantiation to compute Fibonacci numbers at compile time. This technique uses template metaprogramming combined with consteval to perform computations that would traditionally be done at runtime. The template parameter n determines which Fibonacci number to compute, and the function recursively instantiates itself with decreasing values of n until it reaches the base case. These examples demonstrate how consteval can be combined with templates to perform complex calculations during compilation, eliminating runtime overhead entirely. Each template instantiation creates a unique consteval function that is evaluated at compile time, and the results can be used in other constant expressions or as template parameters themselves. Consteval can also be applied to class constructors, ensuring that objects are initialized at compile time. In this example, the typeID class has a consteval constructor, which means objects of this type must be initialized with constant expressions. Attempting to initialize a typeID object with a runtime value will result in a compilation error. This is particularly useful for creating type-safe IDs or resource handles that must be known at compile time. When using consteval constructors, remember that all arguments must be constant expressions, and member functions can also be marked as consteval to ensure compile time behavior for the entire class. One important consideration is that objects with consteval constructors can only be used in constant contexts. They cannot be created at runtime. This makes them suitable for use as global constants, in static_cert expressions, or as template parameters, but not as local variables that would be created at runtime. Another interesting pattern is to use consteval constructors to perform validation at compile time, similar to how we use consteval functions with static_cert earlier. For example, you could have a consteval constructor that checks whether a value falls within a valid range, and the compilation would fail if an invalid value were provided. One of the most powerful applications of consteval is for compile time validation, especially when combined with static_assert. In this example, we have a consteval function that validates buffer sizes, and we use static_assert to check this validation at compile time. If someone tries to create a buffer with an invalid size, the compilation will fail with a clear error message. This approach catches errors early in the development process, before the code even runs. It's particularly useful for validating configuration parameters, array sizes, or any other values that should be known at compile time. The combination of consteval and static_assert creates a powerful validation system that can catch many common programming errors before they manifest as runtime bugs. This pattern can be extended to more complex validation scenarios, such as checking that configuration parameters are consistent with each other, that resource identifiers are unique, or that mathematical constraints are satisfied. By performing these checks at compile time, you can ensure that certain categories of bugs simply cannot exist in your running program, which can significantly improve reliability and reduce debugging time. While consteval is a powerful feature, there are several common pitfalls to be aware of. First, you cannot pass runtime values to consteval functions. This will result in a compilation error. This means that consteval functions have limited applicability in contexts where inputs might not be known until runtime. Second, consteval cannot be used with virtual functions, as virtual dispatch requires runtime polymorphism. This is because virtual function calls are resolved at runtime based on the dynamic type of the object, which conflicts with consteval's requirement for compile time evaluation. Third, debugging consteval functions can be challenging since they're evaluated at compile time, and error messages can sometimes be difficult to interpret. Compile time errors in consteval functions often manifest as template instantiation errors or other complex compiler diagnostics, which would be harder to understand than runtime errors. Finally, there's a tendency to overuse consteval when constexpr would suffice. Remember that consteval should be reserved for cases where you specifically need the compile time guarantee. Using consteval unnecessarily can make your code less flexible and increase compilation time without providing significant benefits. A good practice is to start with constexpr and only upgrade to consteval when you have a specific reason to require compile time evaluation. Let's look at some practical real-world applications of consteval in more depth. The first example shows compile time string hashing for resource IDs, which is commonly used in game development and resource management systems. In this pattern, string literals are hashed at compile time to produce integer identifiers, eliminating the need for runtime string comparisons and reducing memory usage. The hash values are computed during compilation and embedded directly in the binary, resulting in zero runtime overhead for these operations. The second example demonstrates type-safe configuration validation, where critical parameters are checked at compile time. This ensures that invalid configurations cannot even compile, preventing a whole class of runtime errors. For example, you could validate that port numbers are within the valid range, that buffer sizes are positive, or that mathematical constants satisfy certain constraints. The third example shows how consteval can be used for template metaprogramming, such as computing factorials at compile time. This pattern can be extended to generate lookup tables, perform complex mathematical calculations, or implement compile time algorithms that would otherwise require runtime computation. These examples illustrate how consteval can eliminate runtime overhead while ensuring correctness, making it valuable in performance-critical applications such as games, embedded systems, and high-frequency trading platforms. To summarize the key points about consteval in more detail, it's a C++20 feature that declares immediate functions, which must be evaluated at compile time. The term immediate function reflects the fact that these functions are evaluated immediately during compilation, as opposed to being deferred to runtime. The primary difference from constexpr is that constexpr allows both compile time and runtime evaluation, while consteval requires a compile time evaluation. This makes consteval a stronger guarantee, but also more restrictive in terms of where it can be used. C++23 introduced if consteval to help constexpr functions safely call consteval functions when in a constant evaluated context. This feature bridges the gap between the two, allowing for more flexible code that can still take advantage of consteval's guarantees when appropriate. As a best practice, start with constexpr and only upgrade to consteval when you specifically need the compile time guarantee. This approach gives you flexibility by default while still allowing you to enforce compile time evaluation when necessary. Consteval is particularly useful for compile time validation, where it can catch errors before runtime, type ID generation, where consistency across translation units is important, cryptographic hashing, where pre-computing values can improve performance, and ensuring zero-cost abstractions, where any runtime overhead would be unacceptable. For those interested in learning more about consteval and compile time programming in C++, here are some valuable references with more detail about their content. The first article from Medium provides a beginner's guide to consteval in C++20, covering the basics with clear examples and explanations suitable for those new to the feature. The second article discusses the C++23 if consteval feature in detail, explaining its motivation, syntax, and use cases, and how it improves upon the previous STD is _constant_evaluated approach. The third article from Modernizing C++ compares constexpr and consteval functions in depth, providing detailed examples of when each is appropriate and how they interact. The Stack Overflow discussion provides additional insights from the community, including practical experiences and edge cases that might not be covered in official documentation. The C++ Stories article compares all the const-related keywords in C++20, const, constexpr, consteval, and constant, helping to clarify the distinctions and appropriate use cases for each. And the final article from Andreas Fertig's blog demonstrates a neat trick with consteval, showing how it can be used to initialize local non-constant variables at compile time. These resources provide more in-depth information and different perspectives on using consteval effectively, and I recommend exploring them for a deeper understanding of this powerful feature. To understand consteval, it's helpful to look at the historical evolution of compile time programming in C++ in more detail. C++11 introduced constexpr, but with significant limitations. Constexpr functions could only contain a single return statement. This meant that many computations couldn't be expressed as constexpr functions, limiting their usefulness. C++14 relaxed these restrictions, allowing loops, conditions, and local variables in constexpr functions. This dramatically expanded the range of computations that could be performed at compile time, making constexpr much more useful in practice. C++17 added constexpr if, which improved template metaprogramming capabilities by allowing conditions to be evaluated at compile time, with only the true branch being instantiated. This feature made it easier to write templates that could handle different types efficiently. Finally, C++20 introduced consteval and constant, providing stronger guarantees about compile time evaluation. Consteval ensures that a function is always evaluated at compile time, while constant ensures that a variable is initialized at compile time, though it doesn't require the variable itself to be constant. This progression shows how C++ has gradually expanded its compile time capabilities, with each standard adding more powerful features. Consteval represents the current state of the art in guaranteed compile time execution, and we may see further enhancements in future C++ standards as the language continues to evolve toward more extensive compile time programming support.